Section 13.2, limits and continuity of multivariable functions. So let's begin with the limits. So here's the definition of the limit of a function in two variables. All right, goes like this. Let f be a function of two variables, so we have f of x, y, be defined on an open disk centered at the point x naught, y naught, except possibly at x naught, y naught, okay, so it's defined for every point on this disk except possibly the center of the disk. And let L be a real number. Okay, then the limit as xy approaches x naught, y naught of f of xy is equal to L if, okay, for each epsilon greater than 0, there's a corresponding delta greater than 0, such that, ST for such that the absolute value of f of xy minus L is less than epsilon whenever 0 is less than the square root of x minus x naught squared plus y minus y naught squared is less than delta. That's a terrible delta. Let me try that again. It's better. Okay? Okay, so what's this saying? There's a disk in the xy plane of radius delta, and so long as the distance from the point in question, the xy, to the center of that disk, x naught, y naught, so long as that distance, is lying in the disk, so in other words, if the point is in the disk of radius delta, then we can make the distance between f of xy minus L less than any tiny number epsilon. And we can make epsilon as close to 0 as we want, but we can still get closer in. So let me see if I can draw that graphically for you. There's a great illustration in your book on page 885. I will try to recreate that here, but it might be best if you could look this up, but we'll see what we can do. Okay, so in 3 dimensions, right, suppose I've got some surface. Okay, so there's my surface. And suppose I have a point on my surface right here, and that point corresponds to the point x naught, y naught down below in the xy plane. So I'm just going to bring that right down to here. Okay, then I'm going to put a circle, an open circle, a disk, if you will, an open disk of radius delta around that point in the xy plane. Then I'm going to select another point, another xy point here. So let's choose one inside of this disk. That's what this up here means, where that distance formula is less than delta. It means we're inside of the disk of radius delta. So this is xy. Okay, and it has a corresponding point on the surface right here. Okay, so the idea is that as x naught y naught approaches, as xy approaches this x naught y naught, so as it gets closer to x naught y naught, that the distance from this point to this point is staying within this epsilon range. So I'll try to draw that for you here. And just to keep it easier to look at, I'm not going to put perspective on this. I'm just going to draw the z values as if we're looking at this thing at eye level. Okay, so my limit L would be what we're expecting this to be here. So let me go back to white here. So what we're expecting here. So that's L. And then we've got this little range, L plus epsilon and L minus epsilon. Okay. And the idea is that the distance between the point f of xy, so the pink point in my picture here, is going to fall between L plus epsilon and L minus epsilon in that range, no matter what. So as my point gets closer and closer, so as it gets closer and closer to x naught, y naught, my point on the surface is going to remain between this this L plus epsilon, L minus epsilon range. So it's going to kind of stay in between there somehow as we are approaching this limit L. So that's the idea. And hopefully you remember this from Calc 1. That'll make this so much easier for you to understand what's going on here. Now, one major difference between two-dimensional limits and three-dimensional limits is that in 2 dimensions, we don't have any choice how we approach the limit. We are either coming in from the left or we are coming in from the right. Depending on where we are, we don't have any options there, right? So that's it. However, when it comes to 3 dimensions, we're looking for a 3-dimensional limit, I've got 2 variables that I'm playing with. So to get from, I'm going to redraw this, but to get from my point xy to the center of my disk here, x naught, y naught, I have so many different ways I can go. So first of all, one thing I can do is I can say, well, here's my point x naught, y naught right here, or xy rather. Maybe I want to bring that in where x is equal to negative y. So I just say, okay, well, however I'm going to get there, let's just bring it in just like this. Okay. Another thing I can do is I can say, well, you know what, let's walk over until x is equal to 0 and then, or x naught, until x is equal to x naught, and then bring it down. Or maybe I say, well, let's let y go to y naught first, and then we'll let x go to x naught, right? So we've got several different paths that we can take. In fact, there's an infinite number of paths that we can take from the point xy to the point x naught, y naught. Now, a lot of times we know our limits are like, what's the limit as it goes to 0, 0? Maybe I can let x be equal to 0 first, so I'll take x over to 0 first along the surface, and then I'll choose to let y go to 0, or vice versa. So we have these infinite number of paths, and if I were to find any 2 paths that do not go to the same point, to the same limit, the limit does not exist. So let me write that really quickly. Let me write that down really quickly here. All right, so because we are on a surface, let's go back to white here. Because we are on a surface, the statement x naught, y naught, xy approaching x naught, y naught, that means that we can approach that point from any direction that we choose. Okay, so xy can approach x naught, y naught from any direction. Okay, so in other words, there are multiple paths. There's an infinite number of paths, i.e., there are an infinite number of paths from xy, try that again, xy to x naught, y naught. All right, so if the limit as xy approaches x naught, y naught of f of xy is different for any 2 paths, the limit does not exist. For any 2 paths, the limit does not exist. Okay. Oh, I forgot to say is different. Ha ha ha. Not funny. Is different for any 2 paths, then the limit does not exist. And we're going to see an example of this in just a little while, to where we're going to show that the limit does not exist by showing it goes to 2 different places. But before we get to that, just analogously speaking, so analogously, in 2 dimensions, recall if we had a curve that came to this point and then began again here, right? We know this limit does not exist at a. So the limit, if this is, g of x here, the limit as x approaches a of g of x does not exist because the left hand and the right hand limits don't match up. Okay, so because the limit as x approaches a from the left of g of x is not equal to the limit as x approaches a from the right of g of x. So hopefully that helps you make more sense of what I was just saying about the paths. The problem is there's not just a left and a right, there's an infinite number of paths and we can choose several of them. The general ones we choose are to let x go to x naught first, see where y takes us. Let y go to y naught first, see where x takes us. Let x go to y and then let y go to y naught, or vice versa, let y go to x and then let x go to x naught. So there's lots of different approaches we can take there. And those are the most common, but we cannot assume. So let me back that train up just a second. Let me explain what I'm thinking. In this situation, in 2 dimensions, if the left hand limit equal to the right hand limit and the value of the function existed and was equal to that limit, we were done, right? Because those were our only options. But now we have an infinite number of options. So showing that the limit approaches a certain number from any number of paths is not good enough. It's not going to help us prove a limit exists. To prove a limit exists, we could use the definition, or we have other ways to do that as we had done in the past. But if there's any ambiguity, does the limit exist? Okay, does the limit exist? We cannot tell that just by finding paths going to the same point, because there could always be one that we haven't found that doesn't, and that shows us that the limit does not exist. So this method is not used to prove a limit exists, this whole path thing. This path thing is used to show a limit does not exist because I found a path that took me to one point and then a path that took me to another point, so clearly the limit does not exist. I hope that made any sense. If it did not make sense, there are tons of great resources online I recommend you look into. And of course, you can always email me with questions and we can talk about it during our Q&A sessions. Okay, so back to the definition of the limit. I am not going to test you on this. I'm not going to test you over the definition of the limit. You do not have to find limits using the definition on the exam. So rest assured, that's not going to be a problem. But I do want you to see one. So let's go ahead and do what I hope is going to be a fairly obvious example. So example, verify the limit using the definition. Okay, so we've got the limit as xy goes to ab of x is equal to a. So hopefully that's a fairly obvious limit, and we can all just kind of look at that and be like, oh yeah, that's got to be true. And let's go ahead and use our definition to verify it. So we are going to let f of xy be equal to x. All right. Then our limit L is equal to a. We have to show that for any epsilon greater than 0, there exists a delta neighborhood, but a delta about AB such that 0 less than the square root of x minus a squared plus y minus b squared is less than delta will imply that the absolute value of the difference between f of x, y, and the limit is less than epsilon. All right, so let's begin with the epsilon piece of it and see if we can find a delta that will work for us. All right, so the absolute value of f of x, y minus L. That's equal to the absolute value of the function, which is x, minus the limit, which we're saying is a. Okay, and we need to figure out a delta that we can come up with so that our scenario is accurate, so that when we are within that delta, our limit, the difference from our function value and the limit is less than epsilon. All right, so we need to build up towards delta here. Well, one thing that you may or may not recall is that the absolute value of x minus a can be rewritten as the square root of x minus a quantity squared. Yes, because if you have the square root, I'll just write this right up here in the margins. If you have the square root of x squared, that's equal to the absolute value of x. Okay, all right. So that can be rewritten in this way. And that's nice because we're trying to find this delta that will work for us. And we just need x minus a squared plus y minus b squared to be less than delta. So notice that the square root of x minus a squared is always less than or equal to the square root of x minus a squared plus y minus b squared. So let's keep going here. This is going to be less than or equal to the square root of x minus a squared plus y minus b squared. Okay, well, that is what's less than delta. So as long as we let delta equal to epsilon, we're good to go. So let delta be equal to epsilon. Then, exactly what we have here, the absolute value of fxy minus L is equal to x minus a, which is equal to the square root of x minus a squared, which is less than or equal to the square root of x minus a squared plus y minus b squared, is less than delta, which is equal to epsilon, and our limit is verified. All right, but as I said, I am not going to be testing you on the epsilon delta definition of the limit. I'm just going to be looking more for your ability to use it functionally, like to find limits functionally. So let's go ahead and talk about different ways we're going to find limits here. So, to find limits, of course, we can use the definition. It's always an option. Okay. We can verify it using the definition. We would have an idea of what we wanted our limit to be as we went into that. 2, to find the limits, we can use direct substitution. Okay, now this direct substitution assumes that the limit, or that the point that we are approaching, that is in the domain. So that assumes the point that we're approaching is in the domain of the function. Okay, we can't go plugging in things that aren't in the domain. All right, number 3, squeeze theorem. We can use the squeeze theorem. Okay, so remember the squeeze theorem. If we found something that the limit exists that's greater than consistently and something that the limit exists that is consistently less than, then if those two limits are the same, the thing in between has no choice but to go to that same place. All right, and number 4, we can change coordinates. Sometimes it's just easier if we change coordinates. Okay, so that's pretty interesting. Let me give you an example of that one. So let's take a look here. So example, change the polar coordinates to find the limit. Okay, so suppose I ask you to find the limit as xy approaches 0, 0 of the function x squared plus y squared over sine of x squared plus y squared. All right, well, in polar, that would be the limit as r approaches 0 of r squared divided by sine of r squared. And there are several ways that we can show this limit exists. I'm just going to do it with L'Hopital's rule because this satisfies the conditions of L'Hopital's rule. I've heard arguments that you can't use L'Hopital's rule if sine is involved because that's part of it, and et cetera, et cetera. However, L'Hopital's rule is a verified result. I have a function that meets the criteria of L'Hopital's rule. I don't see any reason why I can't use it here. So by L'Hopital's rule, this is going to be equal to the limit as r approaches 0 of 2r divided by 2r times sine of r squared, times sine of r squared, cosine of r squared. All right, so that's going to be equal to the limit as r approaches 0 of 1 over cosine of r squared. And the limit as r approaches 0 of cosine of r squared is 1. 1 over 1 is equal to 1. So there we have found the limit very easily simply by changing the coordinates. Okay, so now let's do one where we can use direct substitution. So example, let's find the limit as xy approaches the point 1, 2 of 5x squared y divided by x squared plus y squared. Okay. The only thing not in the domain of this function would be the point 0, 0. Everything else is valid. So 1, 2 is certainly valid. We can just plug that in. So this limit is equal to 5 times 1 squared times 2 divided by 1 squared plus 2 squared. So that's equal to 10 over 1 plus 4 is 5, which is equal to 2. And there's our limit. All right, so let's take a look now at this example. How about the limit as x, y approaches 0, 0 of 1 over x squared plus y squared? Again, this one can easily be done if we were to switch to polar coordinates. However, before we do that, I just want to discuss what's happening. We have a denominator that is positive or 0. Right? No matter what x, y's we choose, when we plug those in, we're going to get a number that is 0 or greater. So this number, as x and y both approach 0 in the denominator, is going to become smaller and smaller and smaller, right? So as the denominator gets smaller and smaller and smaller, the quotient becomes larger and larger and larger. And because this is approaching 0, this is going to cause the entire quotient to go to infinity. So this limit does not exist. So 1 over x squared plus y squared will increase without bound as x, y approach 0, 0. Okay, so as that happens, this thing's going to increase without bound. Therefore, there is no limit. The limit does not exist. Please be aware, there is no such thing as a limit equal to infinity. Infinity is not a limit. Infinity is limitless by definition, right? So there is no limit. The limit does not exist. So this goes to infinity. So the limit does not exist. All right, so let's do another problem where it's not so obvious that the limit goes or that the limit does not exist. All right, so let's take a look here at this example. So show the limit does not exist. All right, so we have the limit as x, y approaches 0, 0 of sine of xy over x squared plus y squared. Okay. Okay, so I've got this limit and a situation where I've got sine of xy over x squared plus y squared. The denominator is easily converted to r squared, but the numerator's not. So what we're going to do is we are going to form a path from xy to 0, 0 by holding one variable either constant at 0 or by setting one constant equal to the other constant or equal to the negative, just so long as they're moving, they're both going to 0, 0. Okay, so as the value of x and y change, both x and y are going to 0, 0. So we can form a path from xy to 0, 0 in a couple of ways. Hold x or y constant at 0. Okay, so if I say, okay, well, I'm going to let them go to 0, well, I'm just going to start by letting x go to 0. Okay, no problem. We can do that because our function still exists. We're still on a surface in a neighborhood where the points exist. So we can do that, and then we can say, okay, now what's my limit as y goes to 0? Because x is already there, what's happening as y goes to 0? So that would be one path, and then we could swap it, let y be 0, and let x head that way, and that would be another path. Or, so that's one way. Or we can let x be equal to y, or x equal to negative y, y equal to negative x, because as x approaches 0, y will approach 0, and vice versa. So that will let this happen because they're both going to the same point, since they're both going to 0. All right. Now, if one was going to 1 and one was going to 0, we would have to modify that, right? I would have to say, well, let x equal to y plus 1 because y is going to 0, but x needs to go to 1, you know, something like that. We can find these different methods. And it doesn't have to be linear. We could set up a quadratic function that gets us there. You know, y equal to x squared would work. We could do y equal to x squared. We could do x equal to y squared. Any relationship between x and y that's going to, as one of them approaches the value it's supposed to go to, the other one approaches the value it's supposed to go to. So in this case, both going to 0, as long as x goes to 0, that makes y go to 0, we're good. Or as long as y goes to 0, that makes x go to 0, we're good. Okay, so that's what we're going to do. So let's take a look at what happens when we let x equal to 0. So the limit as xy approaches 0, 0 of my function sine xy over x squared plus y squared, that is going to be equal to the limit as not x, but as 0y, get off there, 0y goes to 0, 0. Okay, because x, I'm just saying, okay, well, let's set x already there. X has already gotten there. We're going to go down the path where x is already 0 and see what we get. So sine of xy over x squared plus y squared. Well, it's not x anymore, right? It's 0. So I need to replace these x's with 0. And what that comes out to be is sine of 0 is 0 over 0 over y squared. Ah, damn, no. Hold on, guys. I'm jumping the gun here. So that's the limit as y approaches 0 of sine of 0 over y squared. Well, sine of 0 is 0. 0 divided by anything not 0 is 0. So the limit as it's going there is 0. Okay, so if that limit is accurate, when I do this from the limit from any other path, really, I'm going to get 0 again. But watch what happens if I change it up a little bit. So now I'm going to let xy go to 0, 0 by first allowing x equal to y. So sine of xy, or x squared plus y squared. So I'm going to let x be equal to y. So then what I get is the limit of yy going to 0, 0 of sine of y times y over y squared plus y squared. So that's going to be the limit. Get out of there. That's going to be our limit as y approaches 0 of sine of y squared divided by 2y squared. All right, and so since this is a limit in one variable, I can use L'Hopital's rule again. So by L'Hopital's rule, I'm going to pull the 1/2 out front, guys, just to get that out of there. So by L'Hopital's rule, this is equal to the limit, 1/2 the limit as y goes to 0 of 2y times cosine of y squared divided by 4y. So my y's will now cancel, and I get 2/4, which is another half. So that's equal to 1/4 times the limit as y approaches 0 of cosine of y squared. Okay, well, as y goes to 0, this goes to 1, and this is equal to 1/4. Except it's not. Hold on. I hope you saw my mistake. I hope you caught my mistake. Here, I pulled this 2 out, right, as the 1/2 in front, but then I left it here when I multiplied it, so this should just be a 2. Guys, I'm so sorry about that. So that should be a 2, which would also cancel, meaning that this is not 1/4, it's actually just 1/2. So my limit is 1/2. So my apologies for that. All right, there we go. There we go. All right, so it's 1/2. So, but it doesn't matter. The point remains that the limit, it does matter. It's very important to do the work correctly. But whether the limit were actually 1/4 or 1/2 would not matter. Because if the limit does not match the first limit we found, the limit simply does not exist. So because the first limit we found was 0, and the second limit we found was 1/2 by following a different path, the limit does not exist. So the limit as xy approaches 0, 0 of sine of x squared over x squared plus y squared does not exist because the limit as xy sorry, I'm thinking how to rephrase that. The limit as 0y goes to 0, 0 of our function, I'm just going to call it f of xy for the sake of ease, is equal to 0, but the limit of yy going to 0, 0 of our function f of xy was equal to 1/2, and these are not equal. So it's kind of like a left-hand limit and right-hand limit not being the same in 2 dimensions. Only in 3 dimensions I've got an infinite number of paths, but I only need 2 of them to show it doesn't work. right? We only need one counterexample to show that it doesn't work, and that's what we found here. Okay, so now let's talk about continuity of a function, of a multivariable function. All right. So continuity is going to be very much like we had seen continuity in Calc 1. If the function exists, if the limit for the function exists at a point and f of that point is equal to that limit, then it is continuous at that point. So I'll go ahead and write down that definition for us. Okay, f of xy is continuous at x naught, y naught if the limit as xy goes to x naught, y naught of f of xy exists, and that limit is equal to the function value at that point. Okay, so if those two things are in place, we have a function that is continuous at a point. So let's do an example really quickly. Example: is the function continuous? I'll just say f of xy continuous at 0, 0. F of xy equal to 2x squared y over x squared plus y squared. So the answer is no. The answer is no, because f of 0, 0 would be equal to 0 over 0, which is undefined. Okay, but this discontinuity is a special kind of discontinuity called a removable discontinuity. All right, and I'll show you why. Because the limit at this point does actually exist. And we're going to show that that limit exists using the squeeze theorem. Okay, so the squeeze theorem to find the limit. Okay, so f of x, sorry, back that train up. We're looking for the limit as xy goes to 0, 0 of 2x squared y over x squared plus y squared. Now we are looking for this limit as we approach 0, 0. So I want you to think of these things in terms of numbers that are small, less than 1. Okay, so we're going to zoom in to xy pairs such that x squared plus y squared is less than 1. There's no reason for us not to do that. We don't care what happens far away from 0. We only care what happens close to 0. And that's a 2, not a prime. Okay. So that's what we're going to do. We're going to zoom in on that. And that's important for the second part of this, of the squeeze that we're going to do. So first of all, notice that for all x in the real numbers, 2x squared y over x squared plus y squared is going to be less than or equal to 2x squared y over x squared for all x and y in the real numbers. Okay, so if you make the denominator bigger, you make the number smaller, period. That does not change no matter how big or small the numbers are that we're working with. Okay, so we can find the limit as xy goes to 0, 0 of 2x squared y over x squared. Okay, that's going to be equal to the limit as xy goes to 0, 0 of just 2y, because the x squares will cancel because we're not to 0 yet. We're headed that way, and any number not 0 divided by itself is just 1, and so those are going to cancel away. Going into 0, this comes out to be 0. Okay, so for this function that is always larger than our original function, the limit at 0 is 0. All right, so we had a function that was larger than the function that we were trying to show the limit of. Now we need a function that's smaller. So we need to find something so that 2x squared y over x squared plus y squared is actually larger than another function, some smaller function. Okay, so notice that because we are close to 0 and we're looking at numbers that are less than 1, for all y less than 1, let's say absolute value for, you know what, I'm getting tongue-tied. Let me try that again. For all y such that the absolute value of y is less than 1, multiplying this thing by a y will actually make it smaller. So 2x squared times y over x squared plus y squared times a y is going to be smaller. So that's 2x squared y squared over x squared plus y squared. Now, I would love to be able to simply just do our substitution, to convert our coordinates to polar and had just say, hey, as r goes to 0, this is the case. But the problem is I've got more than just r going on here. When I do a conversion to polar coordinates, x squared plus y squared is r squared, but x squared y squared is not. So we're going to have to be more thorough in our coordinate change. So the limit as xy goes to 0, 0 of 2x squared y squared over x squared plus y squared, okay, that's going to be equal to the limit as x, which is r cosine theta, and y, which is r sine theta, goes to 0, 0 of 2x squared y squared over x squared plus, I need to make the change, don't I? Need to change those coordinates. Okay, so that's going to be 2 times r squared cosine squared of theta times r squared sine squared of theta divided by r squared. Okay, so there we're going to be able to cancel one of those r squares, and that's equal to the limit as r cosine of theta, r sine theta goes to 0, 0 of 2 r squared cosine theta sine theta. Okay, now the thing is I don't have just cosine theta or just r going to 0. I've got r times cosine theta and r times sine theta going to 0. So I'm going to distribute this r squared out a little bit so that I get the limit as r cosine of theta, r sine theta goes to 0, 0 of 2 r cosine theta, r sine theta. Well, as both of those are going to 0, we can see that this comes out to 0. And so we have shown that a function that was larger than our function goes to 0 at 0, 0, and a function that was smaller than our function goes to 0 at 0, 0. Therefore, by the squeeze theorem, the limit as xy goes to 0, 0 of 2x squared y over x squared plus y squared is equal to 0. So the limit here exists. Now, because the limit of f of x, y at 0, 0 exists, but the function, you know what, let's not say the function, that's what it is, but let's define it this way. F of 0, 0 does not exist. The function is discontinuous. It is discontinuous, we know that, but the function has a removable discontinuity. At 0, 0. So that's a special kind of discontinuity. We're going to call that a removable discontinuity because it's continuous everywhere except at that singular point. All right, so just very quickly, I just want to give you some of the properties of continuous functions. These carry over directly from, 2 dimensions, so none of this should be new or surprising to you. So properties of continuous functions. Okay, so given that f of xy and g of xy are continuous at the point x naught, y naught, okay, we have the following. Number 1, for some constant c times f, okay, where c is just some real number constant, that's going to be continuous at x naught, y naught. So multiplying by a constant does not affect continuity. Number 2, if we were to add or subtract f and g, that's going to be continuous at x naught, y naught. Okay, and also multiplying f and g is continuous at x naught, y naught. Oh, just occurred to me, I wrote an extra at up here. It can be very hard to talk and think and write at the same time. Okay, and then of course the division is also continuous provided g is continuous. I mean, g is not 0, is continuous at x naught, y naught, provided of course that g is not equal to 0 at x naught, y naught. In fact, I should probably write it that way. Let's do that. G of x naught, y naught is not equal to 0. There we go. Okay, and I think I'll end this one here. If you have any questions, as always, please let me know.